This is a presentation on waves and optics. How can waves be generated? Waves are generated when energy that is transferred through a medium or space that creates a disturbance that outwardly travels. The wave's type facilitates how the wave in question is produced. The type of waves are mechanical waves such as sound waves, water waves, seismic waves, electromagnetic waves, and waves on strings such as those on instruments. Mechanical waves, sound waves. Mechanical waves need a medium like air or water to operate. Sound and water waves are examples of this. Sound waves are generated by vibration caused by speakers, vocal cords, explosions, as well as many other ways. As the object moves back and forth, air particles vibrate, and when these particles and neighboring particles collide, a series of compressions, which is high pressure regions, and refractions, which are low pressure regions, are created. These travel through the air as a sound wave. An example of this is speaking. Mechanical waves such as water waves. Water waves are generated by wind, objects dropping in water, boats moving through the water, or earthquakes that may happen under the ocean. The wind that blows across the water's surface creates waves that are usually quite subtle. Objects that are dropped into the water disrupt the calmness and creates ripples across the surface. Boats that move through the water produce wake waves due to the boat cutting through the body of water, leading to cascading waves. Earthquakes and volcanic eruptions that take place underwater create large amounts of energy to be expelled, which can also cause large waves known as tsunamis. When the energy is added to the water, the particles that make up water move in a circular up and down motion, pushing the energy all the way across the surface. Seismic waves. Seismic waves are generated when energy is suddenly released onto the earth during an earthquake or something similar. When tectonic plates in the Earth's crust are subjected to large amounts of stress, they can eventually slip along a fault line. The sudden movement releases large amounts of energy which travels through the earth as a seismic wave. Other causes are things like volcanoes erupting or a meteor hitting the earth, creating a giant wave of energy. Electromagnetic waves. Electromagnetic waves are generated when electric charges accelerate either by changing the direction or speed. As a charged particle accelerates, this creates a changing electric and magnetic field. Changing field are produced by each other and can travel outwards toward or through space, and this is called an electromagnetic wave. Waves on a string. Waves on strings are generated when strings become displaced from their original resting position and then are either released or continuously plucked, like for example a guitar or harp. By the plucking of the strings, the potential energy is stored in the stretched string, and when released, the string accelerates back toward the original resting position. And due to the inertia, the string overshoots the resting position, leading to the tension in the string becoming pulled back. This back and forth motion creates a transverse wave that travels along the string. And because this instrument usually is connected on both sides, the back and forth creates when the wave reaches one side, it will reflect back, making both waves combine together to form a standing wave. This is the phase difference between transverse and longitudinal waves. For transverse waves, the phase difference is a measure of how far apart the 2 points are in the cycle of oscillation. For half a cycle apart, it's 180 degrees. For a quarter cycle apart, it's 90 degrees. If they are one wavelength apart and have a phase difference of 360 degrees. For longitudinal waves, such as sound, particles travel to the direction of the sound. The meaning of the phase difference is the same with transverse wave, as it tells you that if one particle oscillation leads or lags behind another, and for how much. An example of this is that the 2 particles at the center of adjacent compressions are 1 wavelength apart are in phase. The difference between the two, with mechanical and electromagnetic waves being either longitudinal or transverse, as transverse or longitudinal waves are based on the direction that the particles oscillate, Mechanical and large-scale waves are based on whether a medium is needed. Frequency in regard to wave motion. Frequency tells you how often an event that continuously happens occurs. It is the number of complete waves or oscillations produced, and those that have complete past the point in 1 second. What this means is that a frequency of 10 Hz will produce 10 complete waves every second. For sound waves, and a higher frequency means higher pitch. That can be anything from a wail to a screech. For electromagnetic waves, that higher frequency means from more energy is released. Time period. Time period is time taken needed for one complete wave, also known as oscillation. The time period is not just used for waves, but also any repeating motion. An example of this is a pendulum swinging back and forth, or a guitar string being struck when the guitar string vibrating when struck. If one wave takes 0.5 seconds to pass a point, then the time period is 0.5 seconds. The effect of this is that a short time period means that the waves are being produced quickly, but a long time period means that the waves are being produced more slowly. This is a calculation for frequency and time period. These are other formulas for the wave speed formula and the frequency and time period formula. An example of how to find wave speed and frequency. How to find wavelength and frequency from time period, and how to find time period from frequency. Optics. Optical reflection. Optical reflection is the bouncing back of light when it strikes a surface such as a mirror. A mirror works by reflecting light, as when the light hits the mirror, they are reflected, hence the law of reflection. The law of reflection is that the angle of incidence equals the angle of reflection. An example of this is when you look in a mirror and you can see yourself. Angle of reflection. The types of reflection. There are two different types. There's regular reflection and diffuse reflection. The regular reflection occurs on smooth surfaces such as mirrors that produce a clear image of what you're looking at, while diffuse refraction is something like a piece of paper. It looks smooth and everything, but it's actually microscopically rough, which actually disperses light into multiple different directions. For refraction. Refraction is the bending of a light when it passes from one transparent medium such as air into glass to another. The light bends because of the speed it travels, changes when it enters a different material. You can see this with a glass of water with a straw in, and the straw in it's straight, you know it's straight, but when you look at it from the side, it looks like it's bent or at an angle. Lenses and refraction. A lens works by refracting light with either a convex or concave lens. A convex, also known as a converging lens, is thicker in the middle, allowing it to refract parallel light rays so that they will meet at their focal point. This is used in magnifying glasses, microscopes, and cameras, that kind of thing. While a concave, also known as a diverging lens, is thinner in the middle, allowing a diffraction of light rays, causing them to fan out. They're used in glasses for like short-sightedness people, for their reading. Snell's law describes how light bends or refracts when it passes from one medium to another. To remember that the angles are always measured from an imaginary line that you can't actually see, but they are perpendicular to the surface, so you will know. Reflection and refraction. For refraction, this is the angle. These are the different things of how to calculate it. And this is for calculating refractive index and refractive index on the speed of light. This is for the speed of light index. And then for differing wavelengths. Different wavelengths of light have in the same material slightly different refractive indices. Violet light, also known as short wavelength, will refract more, while red light, also known as long wavelength, will refract less. This phenomenon is called dispersion, and which is noticed when white light passes through a prism, and because of the refractive index becomes a wavelength of violet and red. Total internal reflection, or TIR. TIR occurs when light travels in a more optically dense medium reaches the boundary with less optically dense medium, and is reflected completely back into the original medium. This means that no light is refracted from the medium. There are two conditions for total internal refraction to take place. First is that the light must travel from a higher reflective index medium to a lower one. And that secondly, the angle of incidence must be greater than the critical angle. The critical angle is always 90 degrees. Polarization. Polarization is the process of restricting vibrations of waves. They can only happen in one plane or direction only. The only waves that can be polarized are the transverse waves because their vibrations are perpendicular to the direction of travel, while with longitudinal waves, the vibrations are parallel to the direction of travel but are slightly different. Polarization, how it works, is that a light wave normally vibrates in many different planes perpendicular to the direction of travel. It's known as unpolarized light. But a polarizing filter must be placed on it, that allows the vibrations in only one direction to pass through, leading to a result that the transmitted light becomes polarized light. We know that transverse waves are the only ones that can be polarized because light can be polarized, and light is a transverse wave, and that's how we know. The applications of polarization. They can be used in sunglasses, and with sunglasses, the applications of polarization are shown with that of polarized sunglasses that reduce the glare received from reflective surfaces such as water, roads, windows, snow, that kind of thing. The lenses in the sunglasses block polarized light that is horizontal, creating a clearer viewing experience. Cameras also do the same thing. What they do is that they make the skies more vivid, and it reduces reflections, improves contrast, and then you've got section 3. Electromagnetic waves are very varied, and we'll go through this in a second. You've got different types of waves. You've got radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. For radio waves, they have the longest wavelength but the lowest frequency. They travel very long distances and can diffract easily. They're used in radio broadcasting, television, mobile communications, that kind of thing. While microwaves have a long wavelength, but not the longest. They have a low frequency, but not the lowest. They can pass through the atmosphere and be absorbed by water molecules. This is why they're used in microwave ovens to heat up food, but they're also used in satellite communications and Wi-Fi. For infrared radiation, they have a medium-long wavelength and a medium-low frequency. They're associated with heat transfer and they're used in thermal imaging, remote controls, night vision, and heating systems. While visible light has a medium wavelength and medium frequency, it's one of the only ones detectable by the human eye, and it's used in vision, photography, fiber optics, and lighting, so you can actually see. Ultraviolet radiation has a short wavelength and a high frequency. It causes fluorescence and can damage living cells. That's why it's used in sterilization, security marking, tanning, and forensic analysis. While X-rays have a very short wavelength and a very high frequency, they can penetrate soft tissues but absorbed by dense materials. They're used in medical imaging, airport security, industrial inspections, while gamma rays have the shortest wavelength and the highest frequency. They're most penetrating and energetic, and that's why they're used in cancer treatment, sterilizing medical equipment, as well as scientific research. Section 4. A two-source interference pattern is formed when waves from two coherent sources overlap themselves and combine together. These sources have the same frequency that maintain constant phase difference, as when the waves meet, they undergo a superposition, leading to the displacement of adding together. For constructive interference, it happens when a crest meets a crest or a trough meets a trough. The waves reinforce each other to produce a wave with a long amplitude. This creates regions of maxing intensity of bright fringes of light and loud sounds for sound. This is the equation. For destructive interference, it occurs when a crest meets a trough, leading to waves cancelling each other out, produces small to zero amplitude. Regions of minimum intensity are created, which are dark fringes for light, quiet regions for sound. And this is the condition for it to happen. Relationship between source separation, wavelength, and source dimensions. For a clear interference pattern to form, separation of sources and their dimensions must be related to the wavelength of waves. The distance between the two sources should be smaller than the distance to the screen or observation point, as if the sources are closer together, then that means that the interference fringes become more widely spaced. Also, if the sources are further apart, then the fringes would be closer together. For light waves, the fringe spacing is proportional to the wavelength and vice versa, or proportional to the source separation. For wavelength affects the spacing of interference pattern as well, with long wavelength equals fringes farther apart, while short wavelength means that the fringes are closest together. The example of this is red light, which is a long wavelength. It produces a wider fringe spacing in comparison to a blue light. Water waves with large wavelengths produce broader interference regions. Dimensions of the sources, we'll get into that in a minute. The dimensions, the sources must be small in comparison with the wavelength because small sources behave like points. Sources producing well-defined wavelengths. And large sources emit waves from a multitude of different points, causing an overlapping pattern that can blur the fringes. Diffraction and two-source interference of transverse and longitudinal waves. Diffraction is the spreading of waves outwards from when they pass through a gap or around an obstacle in their way. It occurs from all types of waves, including transverse and longitudinal waves. The amount of diffraction depends on the relationship that happens between the wavelength and the size of the gap. If the gap is much larger than the wavelength, then no diffraction actually occurs. But if the gap is about the same size as the wavelength, a significant amount of diffraction occurs. Though if the gap is smaller than the wavelength, then the wave will just spread out more greatly. The effects of diffraction and two-source interference in transverse waves. With transverse waves, such as water waves, they can spread out after passing a narrow opening, and while with light they can bend around the edges, although an effect is usually small due to the light having a very short wavelength, and the effects of it on transverse waves, such as water waves, light waves, are that the regions of the constructive and destructive interference produce a large amplitude and small amplitudes respectively. The effects of diffraction and two-source interference of longitudinal waves. Diffraction is a longitudinal wave, as sound waves will spread around corners through doorways, and that's why you can hear someone even though you can't see them. That's what the saying of sound travels, that's where it comes from. The effects of longitudinal waves, like sound waves being two-source interference, is that when the two sources interfere with each other, the constructive interference appears when the compressions meet other compressions, or alternatively, destructive interference occurs when the compressions interact with refractions. When analysing refraction data, you must look at how the amount of waves spreading can change within the wavelength and gap size. A key principle to remember is that the diffraction is at its greatest when the wavelength is similar to the size of the gap of the obstacle. As the gap width decreases, diffraction increases. The wave then spreads out more, passing through the gap, and when the greatest diffraction occurs is when the gap width is at its closest to the wavelength, and that the longer wavelength spread out more, while the opposite is true for the short wavelength. The wavelength will all remain at a constant 2 centimeters and always remain at 2 centimeters, even with the gap width getting bigger or smaller, it will always still technically be 2 centimeters. And the wavefront will spread out more, leading to an increase in diffraction. These are my references for this presentation. Thank you for listening.